hi. Didn't see you there. I'm Mr. French, your AP Stats teacher. It's time to do some Chapter 6. Boom, baby. Welcome back. Thanks for tuning in. This is Mr. French here, your AP Stats teacher. Really excited to start these next few new vids. So in this lesson, we're going to be talking about random variables. This is chapter 6.1, and this is day 1. Take a look at the learning materials and all the documents on the Google Classroom. So in this particular video, by the end of it, you should be able to compute probabilities using the probability distribution of a discrete random variable. And we're going to be defining all of these words. So we're going to be talking about what a probability distribution is. We'll be talking about discrete random variables. And then also we want to be able to calculate and interpret the mean or the expected value or the mean of a discrete random variable. So discrete random variable is the name of the game for today. Ramsey has to go outside. Let's go and get started. So to introduce this idea of random variables, I want you to consider the following situation. You flip a coin 3 times. Okay, so if we were to flip a coin 3 times, I'm going to do this. I'm going to define an event. So I'm going to define an x. I wrote it kind of funny because this is not your typical x like from algebra. This is an x. So like capital X is usually the notation for a specific outcome in a random variable. I'm going to define x as the number of heads obtained. So if I flip a coin 3 times, x is the number of heads that are obtained. So let's think about this for a second. We could have tails, tails, tails. We could have tails, tails, head. We could have tails, head, tails. We could have heads, tails, tails. We could have tails, heads, heads. We could have heads, tails, heads. We could have heads, heads, tails. And we could also have... So these are the total events, or this is everything that could occur if you flip a coin 3 times. So what I'm going to do is I'm going to create what's called a probability model. And what it does is it takes the value of x and gives each value of x that could occur a probability. And if I were to do this, I defined x as the number of heads that are obtained. And the number of heads that could occur, well, it turns out there are 4 options. So if I look at all the possible outcomes, the number of heads that could occur, well, the first scenario is that I could have 0 heads occur, I could have 1 head occur, I could have 2 heads occur, and I could have 3 heads occur. So these are the values that x could take on. Turns out this x, this idea here, is what's called a random variable. Essentially what it means is that a random variable is something, so a variable, it's not like a variable like in algebra, but it just means that the random variable is some sort of event that takes on a numerical value. And in this case here, there are 4 possible numerical values that this random variable, so it's a number that's produced by some sort of random event, like flipping a coin. So if I look at the total number of outcomes here, the total number of outcomes here is 8. So 0 has a probability of 1/8. 1, getting 1 head, what happened? Here, here, and here. So there's a 3/8 probability of the value of x that I defined here. There's a 3/8 probability that the value of x is 1. There's also a 3/8 probability that the value of x is 2. So x is the number of heads that are obtained. 2 heads, 2 heads, 2 heads, another 3/8 probability. And the last one is a heads, heads, heads. So there is 1 situation out of a total of 8 where this random variable has a value of 3. So a random variable is just the outcome of an event. So it's designating a number to a random event. So this is the probability model for the random variable x. And we're going to do a little more clear definitions here. A random variable takes numerical values that describe the outcome of some chance process and gives its possible values and their probabilities. Okay, so this whole idea here is a random variable. You could also graph this. We could graph this as well, and it would look something like this. And so you can graph random variables as well. If you look here, there's something that I did very, very poorly on this graph. I didn't label it. So let's just say this is the value of the random variable x, and this here is the probability. So this is the probability distribution. This is how the probability is distributed. Notice how the most likely outcomes are 1 and 2. There are a few rules for random variables. Let's talk about these rules for a second, then I'll just kind of think back to this as well. So there are two main types of random variables, discrete and continuous. If we can find a way to list all the possible outcomes for a random variable and assign probabilities to each one, we have what's called a discrete random variable. So in this case here, this is a discrete random variable because I can count the values that it takes on. If you can't count it or if you can't list it, that's called a continuous random variable. So for example, measurements. I can't list all of the possible values of somebody's height. Somebody could be 6.5 inches tall, or 6.51, or 6.512, or 6.513. I can't make a list of all those. That's a continuous random variable. But we're just talking about discrete random variables today. A discrete random variable is something that you can list. You can list all of the values. There are a few rules for discrete random variables. The first rule of having a discrete random variable is that, so rule number 1, and it's that every probability is a number between 0 and 1. And that should kind of make sense from previous ideas in this course. The second rule is that the sum of all of the probabilities in this model has to be equal to 1. And to find the probability of any event, you can add the probabilities together that make up that event. So we're going to take a look at that here in a second. Make sure that you understand these two rules. We're going to take a look at a few questions here. You know, a typical question might be, does this probability model accurately describe the random variable or something like that? Let's go ahead and take a look at Apgar scores. Some of you may not know what that is, and this is going to be a sweet learning opportunity for you. In 1952, Dr. Virginia Apgar suggested 5 criteria for measuring a baby's health at birth: skin color, heart rate, muscle tone, breathing, and response when stimulated. She developed a 0, 1, 2 scale to rate a newborn on each of the 5 criteria. A baby's Apgar score is the sum of the rating on each of the 5 scales, which gives a whole number value from 0 to 10. Apgar scores are still used today to evaluate the health of newborns. But what Apgar score is typical? To find out, researchers recorded the Apgar scores of over 2 million newborn babies in a single year. Imagine selecting one of these newborns at random. That's the chance process here. Define the random variable x as the Apgar score of a randomly selected baby 1 minute after birth. And here are the results. So here are the Apgar scores. I don't know if you folks know what your Apgar score was. I don't know what my Apgar score was. So let's go ahead and play What's Your Apgar Score? I'm going to go ahead and ring a few folks and ask them if they know what their Apgar score was. I'm going to go ahead and call my mom. Hey, what's up?
What's up?
Nothing much. What was my Apgar score?
I don't know. I don't remember. Probably a 9.
Probably a 9. Love it. Thanks, Mom.
What did I tell you last time?
I think you told me, you said something low. But
I think I told you a 2 the first time just to make you crazy.
Right. And that did make me crazy. And that's why I call you every year, once a year, about what my Apgar score was. Thanks for being patient with me. Love ya.
Bye. Love you. Bye.
Bye. Guess who we're calling next? We're calling Dad. Hey, Dad.
Hey, Deej.
Oh, I was just calling to ask you what my Apgar score was.
Oh, God. Didn't you ask me that one time before?
I think I ask you guys every year.
I don't know. What's a good score?
Yeah, just say, I'm not going to tell you what a good score is, so I want you to just say a number.
Because that's different than like your SAT, right?
Yeah.
Let's go 350.
Whoa! That's crazy. Love it. 350. Who knew that it went that big?
Oh, I'm at 3.5.
Oh, that's worse. That's way worse.
I don't know.
No, 350 sounds good. That's great.
I changed it to 3.5.
Mhm.
That's probably more accurate.
No boy. Oh, that's funny.
Yeah. What
Cool.
are you guys up to?
I'm making a video right now. You're going to be featured in it now.
Oh, jeez.
Oh, geez.
All right, buddy.
All right. Well, thanks.
Yeah, thanks for coming.
Yep.
All right, talk to you later.
All right. Love you, Dad.
All right, love you.
Bye. And that is what's your Apgar score. Let's just go ahead and take a look at this example. So the values of the Apgar score go from 0 to 10. We're going to define x. So this is the random variable. And this is a discrete random variable because I can list out the total number of possibilities that x could take on. So the value of x could be 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. The value of x could be any one of these numbers. I have listed them, and so it must be a discrete random variable. The Apgar score of a randomly selected baby 1 minute after its birth. So it says, A, show that the probability model for x is legit. Well, the first thing that we want to make sure is that the probabilities are all between 0 and 1. And it looks like that is the case. So probabilities are all between 0 and 1. We want to show it's legitimate. The probabilities are all between 0 and 1. And then the next one, that's rule number 1. Rule number 2, if you remember, is that the sum must add up to 1. So if we add up all of these numbers, you'll notice that it doesn't add up exactly to 1. It's 0.99. Why do you think it didn't add up exactly to 1? 0.99 is essentially 1. This is a real life example. You'll probably not get exactly 1 in a real life example. More theoretical ones, especially like with the coin flipping, it'll add up to 1. So we're very close to 1. So we're going to say that all the sum of the probabilities adds to 1. And I know it's 0.99, but that's pretty darn close to 1. So we're going to be okay with that. Make a histogram of the probability distribution and describe what you see. So here is a histogram of the values of the Apgar score. It's a really nice looking picture here. Apgar score clearly labeled, probability clearly labeled, reasonable heights. So we've made the histogram of the distribution. We have not described what we see. So remember, whenever you describe a distribution, this goes way back to the beginning of the course. Remember, when you describe a distribution, you have to describe the shape, if there's any outliers, center, and spread. Do not forget to put on your socks and context. The graph is skewed to the left and single-peaked. A randomly selected newborn will most likely have an Apgar score on the high end of the scale, which means that the baby was fairly healthy at birth. From the probability distribution, we see that the median is 8. The spread, Apgar score vary from 0 to 10. Most newborns receive scores between 4 and 10. So make sure that you reference the shape, the center, the spread, if there's any potential outliers here. And then context. Make sure that you mention that these are Apgar scores for randomly selected newborns. doctors decided that Apgar scores of 7 or higher indicate a healthy baby. What's the probability that the randomly selected baby is healthy? So what we're really finding is this. What is the probability that our random variable x is greater than, or it could be equal to, 7? This goes back to probability notation. Remember that we defined the variable x as an Apgar score, so this is another way to write it. Well, the probability that it's at least 7 is going to be the probability of these added up. So these are all healthy babies, and all we have to do for a discrete is add up the probabilities. So here are the probabilities for the random variable x, and if we want that the probability of 7 or higher, so we want it greater than 7 or equal to, so we'll just add up all the probabilities for 7 or higher. So we get 0.908. It's about a 90% chance that a randomly selected baby is determined as a healthy baby under this definition. So now we're going to get to a really, really big idea in this unit, and its expected value, otherwise known as the mean of a random variable. That's the first thing I'd like you to understand, is that expected value is a mean. So in order to introduce that concept, let's think about the game roulette. So if you don't know about roulette, it's that wheel that has, so it's that wheel at casinos that have red slots, black slots, and green slots. On an American roulette wheel, there are 38 slots numbered 1 through 36, plus 0 and double 0. Half the slots from 1 to 36 are red, the other half are black. Both the 0 and the double 0 are green. Suppose that a player places a simple $1 bet on red. If the ball lands in a red slot, you get your original dollar back plus an extra $1 because you won the bet. If the ball lands on a different color, so if it lands on black or green, you lose your $1 bet. So let's define the random variable x as the net gain from a single $1 bet on red. So now we have a random variable. It's a variable, so it's a number that is produced from some sort of random process. So if we look at the probability distribution, or the probability model here, the values are -1 and 1, and then we have the probabilities attached to it. So the question that we're going to ask is, what is the player's average gain? In other words, if they keep playing this game over and over and over and over and over and over again, what should they expect to have at the end of all of those winnings? Well, it turns out that is what expected value represents. It looks like, in the long run, on average, about 18 every 38 times, the person's going to be winning $1. Conversely, about 20 times out of 38 times, they're going to be losing $1. So let's consider what this means here. Their average gain. When we want to calculate the average, we can just add up the numbers and divide by how many numbers there are. So if we wanted to find out the average gain, one thing we could do is you could take -1, this number, plus 1, and then divide it by 2. But that assumes that both of these have an equal chance of happening if we just divide them by 2. They do not have an equal chance of happening. So what we do is we apply these weights. So the average gain, if the game was completely fair, the true average would be 0. However, you're going to be losing a little bit more than you're winning. So we have to apply these probabilities. I like to think about it as like a weight that we put on to each of these. So we're still going to add these up, but we're going to put a little weight on these. In other words, I'm going to put a little bit of a larger weight on -1. I'm going to put its probability. I'm going to multiply that -1 by its probability. And I'm going to apply 1's weight to its probability. So this one's a little bit lighter now. If I multiply each of these values by their probability, I am making it proportional to what we would expect in the long run. If we calculate this value, so if we take each of these values, multiply it by its probability, and then add them together, we get this number. We get -5 cents. This is the average gain of this particular game. Roulette has an average gain per a $1 bet of -5 cents. The big thing here is to notice that it's negative. Please remember that averages are what is something that happens in the long run. This is the average gain. So in the long run, after many, many, many plays of this game, the player should expect to win -5 cents for every $1 bet. And this is the expected value. The expected value of this game, otherwise known as this notation here, is the weighted average. Now the interpretation of this is a little bit different. we would say something like this. After many, many plays of the game with $1 bets, a player should expect to win about -5 cents on each bet, on average. So the average value of each. So after many, many plays of roulette with $1 bets, a player should expect to win about -$0.05 on each bet on average. So some big words here. It's after many, 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 many plays with the context. You have your expected value, and then it's an average number. So it is what happens in the long run. If you go back and take a look at that video where I rolled the die 40 times and you take the average of those 40 numbers, it's going to be about 3.5. So I challenge you to do that, but it should be close to 3.5-ish. So let's take a look at the Apgar score example, and now we're going to look at the expected value of an Apgar score. So we define the variable x to be the Apgar score of a randomly selected baby. What we're going to do here is compute the expected value, and then we're going to interpret it. So to compute the expected value, we take each value times its probabilities. Remember, it's a weighted average, plus this number times its probability, plus this number times its probability, plus ... and I'm just going to put the ... there so I don't write everything down, and I'll put like the last example here, 10 times its probability. So it should make sense. Like, this has such a low probability that I don't want 0 to affect this too much. I don't want 1 to affect this too much. I don't want 2 to affect this too much. So these really weight down those numbers. So if we calculate this, we get 8.128. AP Stats pro tip, never round your expected value. Never round your expected value. So now we're going to interpret this value. What does it mean about these Apgar scores? Well, this means that the mean Apgar score of a randomly selected newborn is 8.128. This is the average Apgar score of many, many randomly chosen babies. If we take many, many, many randomly selected babies, the average Apgar score is going to be 8.128. And we can take a look back at our histogram. So 8.128 is about right here. And that seems like a reasonable mean. And notice how when we do the weighted average, the tail doesn't affect it too much. This seems pretty reasonable. But this is 8.128 is the mean. It's also what's called the expected value, what you'd expect to get on average after many, 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 many samples. Our goals for this video were to compute probabilities using a probability distribution of a discrete random variable, calculate and interpret the mean or expected value of a discrete random variable. Those are our two goals. We've seen an example here. Take a look at the suggested practice for, this is 6.1, day 1 on random variables. Your suggested practice for 6.1, day 1 are these problems here. And then also, take a look at the Khan Academy. There's a lot of great practice problems there as well. Thanks for watching, and get ready for some more videos, baby!